Hello friends, this is your physics Sita ma'am. So today we are going to see energy band diagram about insulators and semiconductors. In last video I done for conductors, right? So today I am going to explain insulators and semiconductors. Yes, tell me. So already I just told you about CB and VB. What is CB and what is VB? CB is a conduction band and VB is a valence band, right? And this EG is nothing but this is energy gap. What is VB? VB is a energy band which are completely filled at 0 Kelvin. That is called valence band. In the case of CB conduction band, energy band above the valence band is called conduction band. So these are closely packed. The group of closely packed energy levels are called energy band, I told you, right, in conductors. So group of closely packed of energy levels are energy band. So here we'll just discuss about the insulators and semiconductors. So what is insulator? Insulator means which does not carry current, right? So we'll just see about EG gap, that is the energy gap value also here. So in the case of insulators, there is a large gap. That is energy gap is greater than 3 electron volt. Energy gap is greater than 3 electron volt. EV is a electron volt between valence band and conduction band. So is there any chances of moving the electrons from here to here? No. But in the case of conductors, when I explained in last video, I told you that energy gap will be 0. So there is a flow of electrons from one place to another place. It is very easy because there is no energy gap, right? So that we have taken that energy gap EG is equals to 0 here. This is for conductors which can carry current. But in the case of insulators, conduction band and valence band, there will be large gap which is there in this, that is EG is greater than 3 electron volt. So the electrons cannot move from valence band to conduction band. The valence band is completely filled while the conduction band is empty. Why? How? Because there is no chances of moving the electrons, right? So this will be completely filled while this is empty, right? The conductivity, what about the conductivity of this case? Conductivity, I told the symbol denoted by sigma. It is very less. Conductivity value is very less. And what about resistivity? Resistivity will be high. If conductivity is less, resistivity will be high, because both are inversely proportional to each other, right? So what is the value for this? Sigma is equals to 10 power minus 11 Simon per meter, that is Simon meter inverse, to 10 power minus 19 Simon meter inverse. So sigma is equals to 10 power minus 11 to 10 power minus 19 because conductivity is very less, right? And what about this resistivity? If this is very less, this will be very high, right? So rho is equals to 10 power, this is minus 11. So obviously here will be inversely proportional, means here will be, this is plus 11, right? Yes, which is in the unit is ohm meter, to 10 power, this is minus 19. So here it will be plus 19 ohm meter. Okay. But insulators can also conduct electricity at higher temperature or at higher potential. Remember that point. Insulators can also conduct electricity at high temperature or at high potential. This is the points. These are the points I told about the insulators. Yeah. So what is the first point I told about insulator? In the case of insulator, there is a large energy gap. EG is large between valence band and the conduction band, and the electrons cannot move from valence band to conduction band. The valence band is completely filled while this conduction band is empty. The conductivity is very less, so the resistivity will be high. Insulators can also conduct electricity at high temperature and at high potential. So these are the points about insulators. Now we'll just see about the semiconductors, dears. It's a semiconductor are the substance whose resistivity lies between conductors and insulators. That's why we are calling this as semiconductors, right? So there is a finite gap, finite but small gap between valence band and conduction band. So energy gap is less than 3 electron volt. Here energy gap is less than 3 electron volt. At room temperature, some electrons acquire enough energy to move from valence band to conduction band. As the temperature increase, more electrons can move from valence band to conduction band, right? And what about this conductivity? Conductivity of the semiconductor increases with temperature, right? If it increases, and what about the resistivity? Decreases. So the value lies between, that is for conductivity, values lies between 10 power 5 Simon meter inverse to 10 power minus 6 Simon meter inverse. What about this resistivity? Rho can be taken as, what is this? If it increases, it obviously decreases. So if it increases, this would be decreases. So what about the value for this? Which is, rho can be taken as, sigma is so much. And what about the rho? It's 10 power plus 5, 10 power minus 6. So here will be 10 power minus 5 ohm meter to 10 power plus 6 ohm meter. These are the points about the semiconductor. So what are the points I told about semiconductors? Semiconductors are the substance whose resistivity lies between conductors and insulators, half. That's why we are calling it as semiconductors. There's a finite but small gap between valence band and conduction band. So the energy gap is less than 3 electron volt. At room temperature, some electrons acquire enough energy to move from valence band to conduction band. As the temperature increases, more electrons can move from valence band to conduction band. So what about the conductivity of semiconductor? Conductivity of semiconductor increases with temperature and resistivity decreases because both are inversely proportional to each other. So the value for sigma, that's a conductivity, is 10 power 5 Simon per meter to 10 power minus 6 Simon per meter. So the resistivity is opposite to this. That means rho can be taken as 10 power minus 5 ohm meter to 10 power minus, that is a plus 6 ohm meter. So we just saw about insulators and semiconductors from energy band diagram. I hope you all understood, dears. Thank you.